Hi everyone. Yes, welcome again to ClimTip webinar series. For those who are new to ClimTip, ClimTip is a research project founded by the European Union on the uncertainty-aware quantification of climate tipping points in the Earth system. And today we have our guest speaker, Alexander Robinson from Alfred-Wegener-Institute in Potsdam. He will talk about the stability of the Greenland ice sheet, giving us the big picture. To quickly introduce you to our speaker today, Alexander Robinson is a climate scientist and glaciologist specializing in three key areas of research, from Earth system complexity, climate extremes and risks, to energy system resilience. In 2023, he joined the Alfred-Wegener-Institute in Potsdam as a senior scientist, where he leads the Earth System Complexity Group, and his work focuses on understanding the intricate connections between large-scale components of the Earth system and exploring its long-term evolution, both in the past and into the future. Before that, he spent over a decade at the Complutense University of Madrid, where he began as a postdoc researcher in 2011. And in 2018, he became an assistant professor in the Paleo Modeling and Analysis Group within the Department of Earth System Science and Astrophysics. And in addition, he is also, since 2021, he's served as an associate scientist at the US National Science Foundation's National Center for Atmospheric Research. So without further ado, please welcome Alexander Robinson.
Thanks very much, Gord. Thanks for that nice introduction and also inviting me to speak today. Today I wanted to take the opportunity to step back a little bit and not talk about exactly some specific new results, but actually look at what I say here is the big picture, which is mainly just not looking at the future only, but also taking a look at the past. And hopefully, well, maybe it will be a bit of a provocative talk because I want to highlight mostly things that we don't know or we think that we're trying to quantify, but actually we're missing some key information. And I think that that's important to recognize for us to be able to move forward from where we are today. So I'll start out just with a classic slide that I like to show. This figure from the IPCC is really nice, highlighting why ice sheets are tipping elements in the Earth system. And basically that it's a very complex system if you want to model everything that's going on. Particularly if there's interactions with the ocean, which maybe is more relevant in Antarctica. But particularly for Greenland, there's really a lot happening at the surface and at the margin of the ice sheet that's driving its evolution over time. Several of these processes can be thought of as positive feedbacks, which are what drive it to be a tipping element. So the most obvious one being this lapse rate with temperature here that leads to the temperature or the melt elevation feedback, basically that as the ice sheet starts melting for a given perturbation, then it will access warmer temperatures, which will lead to more melt, and etc. And this will propagate further. But I think what's really interesting to point out as well about all these processes is that most of the processes depicted outside of the ice sheet here operating on short timescales, so seasonal timescales are relatively fast. But cumulatively, they work on the ice sheet, and the response of the ice sheet, that's a very inertial body and it's very large, that's on the order of 1,000 years to 10,000 years, depending. And the same is also true for the isostatic adjustment beneath the ice sheet. So you have this combination that leads to very complex behaviors and a challenging system to model, to put it simply. Not that we haven't tried. So in fact, we've had a good idea that the ice sheet is a tipping element, as we call it now, since already the 90s when modeling started of the Greenland ice sheet. So this is a seminal paper from Letouillier et al. In 1991, and one of the first papers to really show that Greenland had different stable states as temperatures went up. And importantly, also that it exhibited hysteresis, namely that once the Greenland got smaller and the conditions changed, bedrock uplifted, precipitation changed, then it's much harder to grow the ice sheet and it has to go back to cooler temperatures before it can regrow. We went a bit further, a bit later in 2012. We simulated the ice sheet now with coupled with at least a simple regional climate model where we tried to capture some of these positive feedbacks better at the surface. And we ran these quasi-equilibrium experiments where we really very accurately tried to map this stability phase space. And we did find indeed that there was an abrupt threshold in temperature that at a certain point, the temperature didn't need to continue increasing and the ice sheet would still melt away on its own. It was also possible to find an equilibrium state that was more exotic, but that was only accessible if the ice sheet partly melted away and then temperatures were cooled again. And then you ended up at this equilibrium point here. More recently, we've done some work with 2 ice sheet models, just looking at that threshold towards melting. And we found very similar behavior, namely that this threshold once again appeared for both models. But what we can already see that's quite interesting is that the threshold was at a much different place. So if we're looking at GMT, for this model is around 2.3 degrees, whereas for this model is around 1.6 degrees or 1.7. So that's a big difference when we're talking about future global warming and what we're trying to do. So it really highlights the fact that there are structural uncertainties and parametric uncertainties that need to be quantified. But just to give an idea of what that looks like with one of these models, so if we know there's a threshold now in regional summer temperature, which I prefer as a control variable, of 1.5 degrees, and we force the ice sheet with 3 degrees, so above that threshold, then within about 20,000 years, the ice sheet will first slowly and then more rapidly melt away until essentially an ice-free state. What's interesting is, again, you can access these intermediate states. So if the ice sheet is forced with 3 degrees, but then cooled back down to 1 degree over 5,000 years, then that will halt the melting and it will regrow and it will find a new equilibrium that's smaller than it was before, but nonetheless, it doesn't melt away completely. So there is an ability to halt it's not fully irreversible if you cool back down below that threshold. But these are very specific effects that need to be quantified. What I think came out of this and other work that we have is, okay, yes, the Greenland ice sheet is sensitive to warming. That's clear. So if we just look over the first 5,000 years, if we force the ice sheet with a very high temperature anomaly, the ice sheet will melt within a couple thousand years, almost completely, and with very little uncertainty. Conversely, at low temperatures that are near that threshold, then the timescale becomes infinite. And the same is what we found with the previous work, that in fact, because of the uncertainties in the model and how we're forcing it, this is where it exhibits the most uncertainty in that timescale as well, at those lower temperatures. So that's really important for us to get a handle on what we think the ice sheet might do in the future. And that's one thing that I think hopefully is going to come out of ClimTip, that we're going to be comparing model simulations and be performing more of this work, and into comparison projects like TipMip as well. But the real question there, if you look at all this uncertainty, is say, okay, yes, it is sensitive, but how sensitive? How long will this melting take? And what can we expect in the future? And so for that, I think we should look at the past. And the first thing to do maybe is just to look at the geographic configuration of Greenland. It's a unique ice sheet compared to Antarctica. It's not centered at the North Pole, but it's rather shifted further south, which already means that it's being exposed to warmer temperatures. Interestingly, that also means it's got higher precipitation rates due to the storm tracks here in the North Atlantic. But what's immediately apparent just from this map of present day is that the Greenland ice sheet became more stable than the other Northern Hemisphere ice sheets. And there are no other large Northern Hemisphere ice sheets anymore, despite the fact that there were for a long time in the past. So there's something different about its configuration that allows it to remain. one thing we know, being a land-based ice sheet, is that the surface mass balance is really a determining factor. So here in the south of the ice sheet that reaches below the Arctic Circle, there can be temperatures in July above zero, causing a lot of melt, but there's also a lot of precipitation counterbalancing that. Conversely, in the north, there's not very much precipitation, but that also means that and it's not very warm, but any perturbation higher than that can lead to destabilization. So stepping back even further, I think we're getting a good idea of how the Northern Hemisphere evolved over the last 3 million years, basically when glaciation started. So we have these, for example, Delta 18 records from sea sediments that give us an idea of how the climate evolved. And we have model simulations. So this, for example, is a transient simulation with Climber 2 and interactive ice sheets over the last 3 million years. And it exhibits features that we believe are realistic. So one thing is that there's long time scale cooling due to CO2 decline. And this is actually what really facilitated the first Northern Hemisphere glaciation. That started around 2.7 million years ago here, that we first started seeing large ice sheets in the Northern Hemisphere. And also that these were smaller glaciations and on this 40 kiloyear timescale, but around the mid-Pleistocene transition is then when larger ice sheets began to appear in the Northern Hemisphere, and that continued to be the pattern until today. Now, if we zoom specifically over Greenland, what's really neat is we have a new simulation out by Yoon et al., where they actually use the ice sheets, the transient ice sheet configurations from the Climber 2 simulation, and use that within a transient CSM simulation over these 3 million years. And now we can look at more characteristics. Of course, these are only simulations. But we can see in large part that they do a pretty good job. And what we know from here, from the previous simulations, is that Greenland likely first fully glaciated at about 2.5 million years ago. We can't say very well, based on the resolution of the simulations, etc., whether it maintained that glaciation all the way through, but this was around the first time that it first reached its full configuration. Then zooming into the last million years, which is actually what I really want to talk about today, and so this will be the focus of my talk. So it was a roundabout way to get here. Is Greenland over the last million years. So this is the temperature anomaly around Greenland as simulated by CSM. I would point out that the red record is from the North Grip ice core, and so we should know that that only goes back to 125,000 years. And this green record is a synthetic record of Greenland, which is based on the Antarctic ice core record, which is much longer, and it has a relationship to the Greenland temperature anomaly. So in tuning that to match, we can get a first order estimate of what happened in reality. And we see that the simulation, again, does a pretty good job over this million-year timescale. Starting from this framework, we can know that there's at least 3 warm interglacials in Greenland during the last million years that I would highlight. One is Miss 11, so that's the longest interglacial period that we expect over this last million years, although it was relatively mild in global mean temperature. There's Miss 5, or the Eemian interglaciation, about 125,000 years ago, that was much shorter, but probably much more intense than Miss 11. And of course, we shouldn't forget about the most recent one, which is Miss 1, or the Holocene interglacial that we've just been going through now, where actually there was warmer than present temperatures early in the Holocene, so about 10,000 years ago, which led to changes in the ice sheet as well. So I'd like to look at those 3 interglacial periods and just ask the question, how did the Greenland ice sheet evolve in warm periods during this last million years? So starting with the one most recent, the Holocene interglacial, first, I would point out the global mean temperature anomaly during the Holocene. So the maximum temperatures that we've seen are estimated at somewhere between 0 and 1 degrees. So we could consider this a mild interglacial period. It wasn't much warmer than it is today globally. There's a big asterisk associated with that, and I would just show this figure from Alfred-Wegener in 2022. There have been a lot of attempts now to estimate what the global temperature anomaly was during the last interglacial period, so the last 12,000 years or so. And many of them use similar methods, so data assimilation and using paleo data, et cetera, and they vary wildly in their estimates. And we can additionally note that the climate models also are struggling to match what these reconstructions show. So already starting from there, even in the best case that we have Miss 1, it's the most recent interglacial period, there's still quite a bit of uncertainty. But collapsing that down to one curve for the Greenland summer temperature. So this is one estimate from Christo Wizard in 2018 using some data simulation and a CSM simulation. They estimate the summer temperature anomaly, so the peak warming, not more than 2 degrees in the early Holocene. But there's a strong spatial variation as well that we know from other reconstructions. What we do know much better for the Holocene is the reconstructed elevation changes that are available from several ice core locations. So if we just get a picture of Greenland here with several ice cores located largely along the ridges or the summit. And we know that, sorry, time is going the other way in this figure, but that coming into the early Holocene, the ice sheet was apparently thicker in most places than it is today, and then slowly declined in elevation, which is related to that temperature anomaly in the early Holocene. What's also a great resource for constraining ice sheet evolution is relative sea level data through the Holocene, and these are just 2 examples of very specific locations. So these points that we see here show how the sea level evolved in these regions, and we have many data points around Greenland, and those can really help us to constrain the evolution of the ice sheet. I would additionally mention that we have isochrones inside the ice sheet, so we have measured age layers within the ice sheet that can help us, and methods are starting to be developed which can use that as a constraint as well. So if we run some simulations, we can see that Greenland does change a lot. So this is a volume anomaly relative to today for 2 simulations. This reconstruction from Le Cavalier, and then a fully prognostic simulation from Taboni et al. In 2024 last year that we produced. And here we tried to match some of that relative sea level data and also the elevation change in both of these simulations. That was the goal. And we find that essentially Greenland starts from a strongly glaciated state and retreats to below its present day value and then recovers by the present day. So to summarize about Miss 1, we can say that it was relatively uncertain in temperature, but it was likely a mild and short interglacial conditions. But the Greenland ice sheet contributed about 1 meter to sea level above today's level during the mid-Holocene, which we can see here. What I think is really important already to see in this work is that the transient trajectory, as one could expect, the transient trajectory from glacial conditions is very important for how we arrive at this minimum here. And so to just give an example, so here we have a volume anomaly almost the size of Greenland. So this is almost 2 Greenlands in size. And so during the LGM, we expect that the ice sheet actually expanded out to the continental shelf and was much larger than today and contained a lot more volume. And then as temperatures warmed, both in the ocean and in the atmosphere, the ice sheet retreated, and mainly here in this marginal area in the southwest as well as in the north, there was retreat compared to today, and then it regrew to its present day state. But this is a very specific target, and it's obviously dependent on the forcing you apply, but also how that forcing is applied and where you start from. So that's an important thing to remember when doing these paleo exercises. I'll switch now to Miss 5, so the Eemian interglacial, which is has always been an exciting one because there's a lot of ideas that Greenland melted much more during that time because it was warmer. But it's been elusive to actually nail down how much it melted. So this was about 130 to 115 kiloyear ago, and there's ice that's been found at Summit and at Neem that was deposited upstream. Die 3 and Camp Century, these 2 cores here that are more marginal, they show tenuous evidence for ice at the base, but actually there's no climatic information that was retained because those were mixed with sediments at the base. And it's not clear what the source of that ice was. A better idea that we have is that the southern ice sheet remained intact, given a significant glacial discharge into the ocean and only a small increase in pollen. And so this was a nice study using actually sediment core data from this Eric Drift core here. And basically you have ocean currents that are bringing sediments that are discharged into the sea here. And that's what's shown here. So for the Holocene time period, where we know the ice sheet didn't melt too much, and then Ms. 5 here as well. So these colors are associated with these different geological regions. And they're able to show that there's still discharge from the ice sheet occurring from these regions and arriving at this ice core. So that's indicative that there was still ice present. Furthermore, there wasn't a large increase in pollen during this time, so there wasn't a southern Greenland fully covered with forests, for example, although there was a slight increase. So it gives you the hint that maybe it was a bit smaller during Ms. 5, but it wasn't completely gone. It was a warmer interglacial, so we expect that the global mean was around 2 degrees above present, whereas the northern hemisphere reached temperatures of 3 to 5 degrees above present. But the global sea level, we're fairly confident now that it was much higher than today, about 6 to 9 meters above present. And that's large enough that it requires most likely a contribution both from Greenland and Antarctica. So we have confidence that Greenland was smaller than today, the ice sheet was smaller than today, but the constraints that we have are weak and in some cases contradictory, which is what I want to highlight today. What I would show is just an estimate of the Greenland ice sheet sea level contribution during the EMIN for different studies over time. And we see some convergence in the last studies to a relatively low number between 0.5 and 3.5 meters. A lot of this came from information we got from the Neem ice core. This was the first successful reconstruction of ice during the EMIN, so it was actually found in the ice core itself, ice that spanned this time range, and it was very complicated because some of it was folded over, so it had to be reordered to have the right time, or actually the same record was duplicated in some cases. But they were successful in reconstructing that order, and they came up with delta 18 measurements that give us an estimate of temperature changes and total air content, which gives us an estimate of elevation changes with some calibration. What's interesting to note, though, is that this led to the so-called Neem paradox, which is that the reconstructed temperature anomalies, as you see on this figure, are up to 8 degrees above warming, but the elevation change, which is this blue curve here, was very minimal. So the idea was that the ice sheet didn't change that much, despite the fact that we had really strong warming over several millennia on the ice sheet. And this is very hard to explain. Before going further, I would just note that in this figure from the Neem paper, we can see that this gray shaded region is the region of the ice core that they found significant melting in the ice core. So this total air contact signal was completely disturbed, and that's why we have these kind of crazy values during this period. I think they're confident about total air content here and here, and then it was linearly interpolated to give a signal here, and this part was discarded. So it already gives you an indication that there was melting present, so there must have been something happening, at least. But it's difficult to explain. So interestingly, the last studies here in this graph that seem to converge, they all agree with the Neem elevation constraint, and that was taken in the community to be a strong constraint. And that's how we got this convergence. But I think a lot of these studies forgot about temperature, and that's something I want to focus on today. So we can look actually specifically at the temperature reconstructions. That's in this, the gray curve here is the one from Neem. So now actually time is going from left to right. And this is the EMIN interglacial period. And the red dots are from the summit, our data that's from the summit. They're a bit more sparse than the Neem records. But nonetheless, they're quite consistent with each other, which is already interesting. In the background here, we also have an estimate from a climate model intercomparison during this time period that we can see looks quite different than the record over Greenland, actually. So the global climate models, they actually largely follow insolation, which peaks around 126, 127 at these latitudes. And these global climate models also underestimate warming, or put it another way, they're not able to achieve such high levels of warming in the North Atlantic. It's really striking how similar the summit and NEAM delta 18 signals are. Here they're converted into temperature anomalies using this simple factor. And that leads to a warming of about 6 to 8 degrees locally. So either right at the summit or right at the NEAM deposition site, which is a couple hundred kilometers upstream. But I would just note that there's a lot of uncertainty in these delta 18 reconstructions, but interestingly, these anomalies are consistent with other proxies. So for example, mosquitoes that have been found in a lake in northern Greenland that can only live in certain climates. What's really difficult to explain here actually is such late anomalies, right? If we know that insolation peaked here at 126, so without doing any modeling or anything else, we can already begin to wonder what can allow locally high temperatures to persist when insolation has already passed to lower levels than today. But nonetheless, we can go forward with modeling with that thought in mind. And so basically for any model now, we have three nice constraints that we might want to apply. One would be the temperature anomaly as reconstructed at the summit. The temperature anomaly is reconstructed at the upstream deposition point of NEAM. And one would be the elevation anomaly of NEAM. And so we did some simulations with our model and varying some ice sheet model parameters, but actually the driving factor was changing the forcing that we applied to the model, so the regional climate anomaly that we applied. And we found what was our best fit simulation, this thick red one. But we did two permutations. So one, this dashed line, this is the best fit to the summit data, the dashed line here. And what we see is that that one is way too warm for the NEAM data. And the reason it's too warm for NEAM is essentially that the ice melts away completely from NEAM and we end up with ice-free conditions there and it gets very warm. And then conversely, we can look at the elevation data and say, well, we want to match that. And so we can actually find a simulation that matches the elevation reconstruction really well. So only 100 meters of elevation drop during NEAM and regrowth here. The problem is that to maintain that low elevation change, it requires very low climatic forcing to the ice sheet, so around 2 degrees rather than the 6 to 8 that we expect. And that forcing has to finish already by 120 kiloyear, which is in contrast to both of these delta 18 records. So our best simulation is somehow the compromise between capturing the NEAM record, which is quite strong here, but not going too warm to miss the NEAM record so much. So it's a balance between the two. Lastly, I would point out, one could say, well, maybe this is just our model, but if we look at, for example, this simulation that was a very good simulation with a regional climate model driving it from Helsen et al., they had temperature anomalies similar to our low, so about 2 degrees of warming there, that neither captures the temperature anomalies at summit nor at NEAM, but does capture the elevation change quite well. So this would indicate that these models have similar sensitivity as models, and it's really the forcing that's dictating how they respond. So what we can learn from this is that models cannot reproduce both the temperature and the elevation reconstructions. And the insolation peaks at 126 kiloyear ago, but what explains those late Eemian warm temperatures? I think that the temperature reconstruction suggests a large sea level contribution. And that's mainly because the only thing that I know that can explain these late Eemian warm temperatures is an elevation reduction, as we saw here, of about 1,000 meters at NEAM, which can explain this just by lapse rate correction effectively. So looking at that, ignoring the elevation as a constraint, but rather just using the temperature anomalies during NEAM, then we can run our coupled ice sheet model with a regional climate model, and we can find that we we get regional summer and temperature anomalies of about 3 to 5 degrees, so this black PDF that we have here. And that corresponds to a sea level contribution of between 4 and 6 meters, so a best estimate of about 5 meters during Emin. That looks something like these here. That's much different than most estimates we have today, as we saw in that figure. So, and the key difference between that is whether we take elevation as our constraint or temperature as our constraint. The key challenge we have is to either understand why one of those proxies is flawed or understand why models can't capture both. Switching to Miss 11, which is older and maybe more mysterious, but at the same time a little bit simpler to understand because it was so long and the ice sheet melted quite a bit. So it was a very long interglacial, and it had peak global warming of about 1 to 2 degrees above today. So medium intensity, but several kiloyear long, which was enough time to melt the ice sheets. And we know our best estimate is that sea level reached between 6 and 13 meters above present day. So quite a significant level, more than Miss 5. And again, requiring a significant contribution from Greenland. So if we look at how insulation evolved during this time, it was already warm before entering the Miss 11 period here around 420 to 405 kiloyear ago, where there was a significant summer anomaly in this period. This boundary forcing comes from these transient climber 2 simulations that we had, and then in our modeling experiment, we found a way to perturb those temperature anomalies so that we could follow a similar trajectory but force our Greenland simulation with warmer or cooler values so that we could test different forcing levels. One thing we do know about Miss 11, again, from the same study I showed earlier, is that the southern region of the ice sheet largely disappeared, given the fact that there's very weak discharge now into the ocean. So meaning that these sediments weren't arriving at that core, which likely means that the ice sheet was retreated at that point. And there's a massive increase in pollen this time. So this is more than Miss 5 and way more than the Holocene as well. So that gives a pretty good indication that there was large forest growth, and these have to be local sources, according to the authors. So if we look at our simulations then, based on that information, we can run our ice sheet model, and we get a whole spread basically from anywhere from 0 to 7 meters. That was by design. We wanted as cool and as warm as possible to cover the whole range. What I think is quite striking immediately is the fact that the peak warming in our simulations happens here around 411 kiloyear ago, whereas the peak mass loss happens many kiloyear later, so around 403 kiloyear. And it indicates this lag that the ice sheets are induced. So although a climate forcing is imposed here, it takes a long time for that heat to accumulate. Comparing the difference in the ice sheet during that time, you have peak warming, so around 411 kiloyear, and we also ran a vegetation model and found that indeed we were able to grow some forest during this time. Interestingly, when the ice sheet was its smallest was when it was very difficult to grow forest during that time. And that's because by then the climate had cooled a lot and the ice sheet was about to start regrowing. So it would have been too cold for forest, at least according to our simple vegetation model. So again, this is important to keep in mind, but the timing on this type of reconstruction is still quite uncertain as well. So it's difficult to use that as a constraint. Nonetheless, by making an estimate, so looking at panel B here is, we came up with a weighting function for our simulations to say, well, rather than assuming all these simulations are equally likely, rather we can use this information that looking at the fraction of the ice sheet that was ice-free below 69 degrees north, and we just came up with a weighting function that said basically we're more confident or we give more weight to any simulation that shows the ice sheet being ice-free in this period. So when we do that and we do a statistical analysis, we find that our simulations give a most likely estimate of 20% ice covered in the south. And this corresponds to a peak regional summer temperature anomaly of about 2.7 degrees, but a sea level contribution of about 6 meters, so almost completely ice-free during that time. And the difference is largely due to the duration. So this is a lower regional temperature anomaly than the 3 to 5 degrees that we had in Greenland, where we estimated only 5 meters of sea level, but here the duration is much longer. So that's what can explain the mass loss. So it again highlights that fact that the interglacial evolution is really path dependent. And so if in our simulations, which it could easily, ours are driven by these Climber 2 simulations, it could easily have been a little bit warmer during this time. Maybe there was an overshoot and a retreat, and this may have already caused Greenland to retreat much more than it had in our simulations, and it would change the dynamics, the picture of this curve a lot. So I think that that's really a goal for us in the future, is to focus on transient simulations and being able to capture the ice sheets starting from their glacial state. And because I think that's a much stronger target, is going from the glacial state into an interglacial. The last thing I want to talk about today are older interglacials, because I think that's fascinating for Greenland as well. We have even less information. So we have no simulations of the Greenland ice sheet that are specifically available. And we really have no definitive paleo data. So it's very sparse and it has very poor time constraints. So plus or minus 200,000 years we're talking about. But what we do have is very hard to understand. And so I'll just highlight some of that today. One is this paper from Schaefer et al. 2016, where they postulate that Greenland was nearly ice-free for extended periods during the Pleistocene. And they come to this conclusion by looking at bedrock that was recovered from beneath the summit. And then they measured it for cosmogenic nuclide concentrations, which can be used as a proxy for how long and how recently that bedrock was exposed to sunlight, because it's bombarded with cosmogenic particles which produce these isotopes that then decay with a certain lifetime. So you can expect that there's more of these present in this bedrock the longer it was exposed to sunlight and the more recent it was. Based on that data, they come up with basically different scenarios, right, of when. And again, now we have time going this way, so this is 3 million years. And they come up with these 3 scenarios that are listed here, because what they found was that over this time period, this 2 million years, we should expect that Greenland, or the summit rock, was ice-free for 280 kiloyear during that time. So the question is, the simplest one that maybe is not the most likely, is that basically that rock stayed ice-covered for the last 1.1 million years, and then from before that time, there was 280,000 years where it was ice-free. So it was ice-free for a long time, and then suddenly it was ice-covered forever. That would at least be consistent with the data they have, to give you an example. The second data point, the second scenario they come up with is one of minimum stability. So basically every time there's an interglacial, the ice sheet becomes completely ice-free for 20,000 years. And that's what these red bands are here. And so cumulatively, you end up with the same amount of exposure. And that somehow is also consistent with the burial time. This is also difficult to understand. A last one they propose is something like multiple exposures. So maybe earlier in the Pleistocene period, we had an ice-free period in Greenland. Then there was a period of rapid change in Greenland that was becoming ice-free and ice-covered until about MIS 31, which is a candidate for Greenland being strongly affected. And then it was ice-covered except for maybe MIS 11, MIS 9, and MIS 5, right? So that could also be somehow plausible. Although this is also difficult. This is challenging to our interpretation, since, again, we think that Greenland already started glaciating around 2.5 kiloyear ago. And unless we have better data here, it's hard to see how it would have been ice-free for so long. So this is very challenging to understand, unless something in the boundary conditions of Greenland changed, and there have been some exotic proposals about that as well. So I just leave the question there: how are any of these scenarios possible? At least for the modeling world, I would find it challenging to reproduce them. Another interesting study which goes in this direction, actually this was from this year, but there were already some previous studies that hinted at this. Again, from the summit, now in that sediment under the summit ice core, they found fossils of plants, insects, and fungi that should be evidence of ice-free time as well, right? So these are actually pieces of wood that they found. This is, they think, part of an eye of an insect that was there. And so these are also, well, kind of obvious markers for an ice-free Greenland at some point. The big question here is, of course, when, at least in this paper, as far as I could tell, they're talking about 2 million years plus or minus 0.4 million years. So that's not wholly inconsistent with what we think if Greenland started glaciating around 2.5 million years ago. But if you try to reconcile this with the previous paper of long exposure, on the one hand, they support each other. On the other hand, the timing is very difficult to reconcile. So I think those are open questions. They're a bit more exotic, but nonetheless important. So I would go to conclusions here. Returning to this picture of Greenland during 3 million years with these three interglacials, very simply, my conclusions could be this, just these question marks. I think that we know a lot less than would seem. We're certainly trying to improve in that respect, but I think that a lot needs to be done on the modeling front to actually be able to do this well. And hopefully we'll have more data to work with to constrain the models. I think we have enough data in MIS 1, so in the Holocene, to constrain our models, but we need to do more work to actually do that well. What we can say is that warm periods existed in the past and that they did impact the Greenland ice sheet. And I would say that the reconstructions hint at a high Greenland sensitivity to warming, in contrast to the consensus that we've been going towards. I think we really are now building the tools to investigate these questions. We're beginning to have fully coupled or system models, including ice sheets. We have the computational power to really do transient simulations during these interglacial periods. And we're going to start using proxies like we're going to use in ClimTip, the isochrones, which certainly for the Holocene should help us to constrain the ice sheet behavior even further. But all of these are valuable exercises, and I think they're really important for us reducing uncertainty in our projections of the future. So better understanding the past stability will lead to more confident projections under future warming. And I would leave it there. Thank you very much.
Thank you so much, Alexander. I was trying to make notes. Wow, when you said the title of the talk and the big picture, I didn't understand exactly what you meant. I didn't know we're gonna be transported to 2.5 million years. Thank you for concentrating only on 1 million years of that. I wonder if you have any questions in the audience. I think Nicholas has, yeah, maybe you could start it off, Nicholas.
I'm also happy to give others the floor first. I have probably questions
Right.
for half an hour. So maybe first, okay, if no one else wants to go first, then I go. Thanks, Alex. I think, yes, I mean, that was a really, really great talk and sort of exactly the kind of talk that we have in mind for these ClimTip webinars. When you said in the beginning that you want to take a few steps back, I was already like, yeah, that's exactly how we imagined this so that sort of get everybody on board. That was really cool. Thanks. Now my question is a little bit more technical. Sorry. So you said, so it was triggered when you said we have more data to constrain the models. Do you mean, how do you specifically mean that? And or could you mean that in a sense of, let's say you have a differentiable model, and then you would basically train that or tune that on sort of paleoclimate data, and then hopefully all the parameters still have a physical meaning, and then you can check whether the sort of resulting parameter combinations would be consistent with sort of basic physics.
I mean, I think it's going in the right direction. So using a differentiable model would just be a more effective way to do what we kind of do in an ad hoc way with these ensembles. The key there would be, so really getting a handle on data that does allow us to filter out and to say that this is a more reasonable set of parameters for our model. So I think for MIS 5, for example, I think that's really the challenge right now, because again, either the data conflicts with itself, or our understanding of the model world is still way too poor. We're missing some key feature of the climate that's changing in that time. But for the Holocene, I think there is hope using these isochrones, for example, that this is a much more complete data set that we have. So there, I think we have the possibility. That said, we've tried working with it so far, and it's more challenging than we thought, mainly because with an isochrone, so rather than just looking at the age layer of year 0, so at the surface, we know how thick it is at the surface. We also know how thick the ice 5,000 years ago should have been. The problem is that that's affected not only by accumulation rates at the surface and then ice dynamics, but also from how well you model the layers underneath. And so if you don't get those right, it's kind of a cumulative problem, and then it can bias you up or down. So it's a challenge in our community right now to figure out the best way to use this information and avoid those pitfalls.
Thanks.
Do we have more questions? I have a question which maybe is kind of simpler and more, yeah, to something, one of your conclusions at the end. You said that the paleo evidence hints at the high sensitivity of Greenland ice sheet to warming. And then you mentioned versus the current consensus, or like, what was that? I didn't understand. Compared to what? Is that in IPCC, or where is that consensus?
So that statement, I was mainly referring to this exercise of constraining simulations of the Eemian interglacial, namely that if we look at elevation changes constrained, then we could say the ice sheet didn't change very much, despite the fact that temperatures were reconstructed to be very high. The alternative view is to force the ice sheet with the high temperatures and then get a simulation that loses a lot of mass and is actually then inconsistent with that elevation change estimate. I think the temperature change reconstructions are more robust than the elevation change constraint at this point. So I think it's better information to go on. But nonetheless, so switching that to then what do we do for the future? In both of those cases, we're using the same model. So far, we haven't really been using that information to throw away model versions or say this model. Most of the models that we've seen running through the Eemian actually show a similar sensitivity. So in that sense, it's not changing our projections. But we need to resolve that conflict of not being able to explain all of this information in order to improve our estimate of the projections, if that makes sense.
I think so, a little bit. Yeah. I think, was it related to one of the graphs when you showed that there's a lag in this temperature rise and then versus the elevation change, I think, was it? It's like thousands of years.
Yeah, that's right. So in the Eemian time period that we had reconstructed temperatures of 6 to 8 degrees around 120 kiloyear ago, but insolation was very low at that point. So there's no reason why the climate would have been warmer itself during that time. The only way you can explain it was with a local elevation change.
Thank you, yeah. Please, Richard, go ahead. Richard Wood.
Great. Thanks very much, Alex. That was a really useful talk from me, who really knows very little about the ice sheet. It's a fantastic survey. So I want to follow on from Quat's question, actually. So if I interpreted your answer right, I think what you were kind of saying was that if one constraints, so of course I'm coming at this from a kind of oceanographer's point of view, like how much fresh water might we expect added to the North Atlantic for a given amount of warming, and I think if I interpreted your answer right, you were saying that if you constrained that based purely on the proxy data, you might come up with an answer, but because of the inconsistency with the models, that might be a little bit too, that answer might be a little bit too confident and maybe too low. And so we should be considering possibilities for that kind of sensitivity that come from models, come from the kind of range of models, as well as kind of purely basing that on the observations. Is that sort of the right interpretation?
I guess what I'm trying to say, so if we look at, maybe I would share one more figure again, and it would be easier. I can share it again. Actually, I should stop it. And then, sorry, if you just give me a moment.
Sure, yeah.
So, yeah, I think this is the best figure to discuss. So the way I would think about it is this, that both of these models, the thick red line and the thick blue line, those are both two different ice sheet models, being forced in different ways. But when they're forced in the same way with low temperature anomalies, they give a similar response: low sea level contribution, low changes in NEAM. So actually, the model sensitivity that we have is pretty consistent with each other. I think that the parametric uncertainty that we have in the ice sheets is large, but on the whole, when they're driven by a strong forcing, they'll do relatively, especially for Greenland, you know, that it's more surface mass balance driving that, right? The trick is that if temperatures were indeed this warm and the elevation is true, then our models we should find a way that these ice sheets are way less sensitive to temperature, right? Because somehow we want the temperature to go this warm and not lose any ice. Maybe one way to do that is that there should be a lot more precipitation happening on the ice sheet during this time period. And maybe that's a way to restabilize the ice sheet without it changing too much. Nonetheless, we still have to explain the fact that the temperature is really warm late in the Eemian. The only way I see to do that is with a strong elevation change at NEAM. So that's what I mean, that until we resolve this inconsistency, it's difficult to use this data to improve our projections.
Yeah. Okay. Yeah. Thanks very much.
I wonder if there are more questions. Go ahead, Jan.
Can you hear me well? Well, thanks, Alex, for the talk. It was great. I mean, you mentioned at the end that we're now going towards a situation where we have the tools to solve some of these issues, maybe by having ice sheet models that are coupled to an Earth system model. So you would reckon that it's a problem that's purely limited to boundary conditions? Because, I mean, there might be also something that is, you know, ubiquitous to various ice sheet models that might be missing some of the ice sheet dynamics, but you rather think it's forcing the boundary conditions, or are we not so sure about that?
Yeah, no, I think that my idea is that certainly we're doing a poor job of simulating the transient boundary conditions. And until we solve that problem, it will be difficult to confront any of the other problems that we have in the models. I think the models certainly can be improved. There's processes that we need to consider, but to the first order here, it's, you know, we need an ice sheet that can start. And that's why I actually think, you know, the Holocene is a really underutilized period for constraining the ice sheet behavior, because I think we have a pretty good idea, or we have a better handle on how it evolved during that time. And it did change a lot. It moved from a continental scale ice sheet down and back up. So this is a really nice test bed. And we just have a framework to transiently force that ice sheet. And so I think that having that coupled approach and then being able to do that in a parametric and exploration really gives us a strong chance at getting it right.
Thanks.
I had one more question, more like world implications of Greenland melting and policy. Policy related questions. There was this in December, this hearing that was brought forward by the Low Island nations in front of the International Court of Justice, right? You might have heard about it. In December, there were 2 weeks of testimonials, and one of their arguments was exactly the melting of the ice sheets as an existential threat to their existence and their culture and livelihoods. What would you, if you were in front of the ICJ, what would you add to that? Or like, what would you comment on that in terms of the fate of the low-lying nations in the Caribbean or the Pacific?
Mm-hmm. Well, I'd have to prepare a lot more if I was confronting the ICJ. But nonetheless, I mean, yeah, one thing is what you can say in a court, and I think that's really the challenge, because here we're talking about effects that unfold over centuries and millennia. So it's really clear that we're driving the system to a place where then it will continuously raise sea level for millennia. So even if it doesn't destroy those low-lying nations next decade or next century, 500 years from now, it will. I don't think we have the legal framework really to address that clearly. So I would simply try to make that message clear that what we are confident about is that these effects will be large and they will be continuous. And what they can do with the information, I guess we'd have to leave it in their hands, unfortunately.
Right. But in terms of the immediacy of the urgency of this sea level rise problem for these nations, you just mentioned this is uncertainty, but like, could you clarify on that?
Yeah, I mean, what I mentioned in the first graphs I showed with temperatures, that, you know, if we do a good job of maintaining low temperature anomalies for global warming, then that uncertainty in sea level rise will really come to the fore, especially on these longer timescales, because a slight perturbation can mean, you know, 1 meter versus 2 over several thousand years or several hundred years even. So from the scientific point of view, I think it would be really valuable to be able to constrain particularly those intermediate range of temperature anomalies. How does the ice sheet react to that? Here we're talking about Greenland, which I think has conceptual dangers to low-lying nations like that. And as I said, we're obviously culpable for what would be unfolding over centuries and millennia. It's also, but at the same time, it's not the clear and present immediate. It's urgent in the sense that we will compound those effects and we need to stop doing it so that it doesn't happen. The immediate danger, the much more immediate danger is coming from Antarctica, I think, in terms of sea level. So here I focus on Greenland, but for a more immediate threat that has similar implications, then I would focus on Antarctica, I think.
Thank you so much. If we don't have any more questions, then I would thank our speaker again, Alexander. Thank you again for a very interesting presentation, and I'll remind everybody else that we will have the March presentation on the approaching tipping points of the AMOC. And yeah, with that, I thank you all for your participation.
Thank you. Thanks very much for organizing.